Yeah, as usual, feel free to stop me whenever you want. So today I would like to discuss two concepts related to the time-dependent perturbation. So one is about quantum quench. Another one is about the linear response. Okay, so let's start with the first one. So whenever we say quantum quench, we means following situations. Let's say originally we have some Hamiltonian H naught, which has some energy levels and the corresponding eigencat. For example, let's denote as cat n, En. You can think of, for example, like an infinite deep well, and there's some levels. Then this is a ground state, first excited state, and so on. Okay, so now we change this Hamiltonian to another Hamiltonian H1 within time tau. So as long as this time tau much smaller than the time scale associated with the energy splitting in our original Hamiltonian. For example, so okay, let's denote as delta E. So in this case, for this kind of a one-dimensional infinite deep well problem, assuming the width is L, then the energy splitting, sorry, the separation between different energies would proportional to something like this, right? As long as this time scale of the change is much smaller than the time scale associated with energy separation, then we can say, okay, this change is a sudden change. And if we prepare our original, our system in the original eigenstate, for example, in the original ground state, then this state has no time to respond to this sudden change. Therefore, this original ground state will evolve according to H1 instead of H naught. Right. This typical problem, this type of problems is called a quantum quench problem or quantum quench dynamics. So from the point of this H1, your original, so this system is out of equilibrium, right? It's not the eigenstate of your Hamiltonian. Yeah. Okay, so is it clear about the definition of this concept? Okay. Yeah, this kind of method is widely used in experiments to study some interesting dynamics.
Is it like the step like time dependent Hamiltonian?
Yeah, basically you can think of your uh, uh, originally you have some H naught, now you change to H1. It's a step like change. But compared with the time-dependent perturbation, this change is not necessarily small. It can be quite large. Yeah. And also the H1 usually is time independent. Okay, so this is also one type of problems that can be present in exam, also in comprehensive exam. Um, even though to solve these problems, you don't need to know the concept of this quantum quench, but for example, the program can tell you, okay, I have a system of with 2L, and now I prepare the original state, sorry, the initial state of my system is in some ground state of um, with this kind of type of wave function, like basically the initial state is in some cat 0 tilde, which is the eigenstate of this H naught, which with L. Now I ask you to calculate the evolution of this state. So I will give you guys an example. I think it's a very interesting example because it will introduce some new concepts. Okay, so this is assuming this is the original Hamiltonian, is a simple harmonic oscillator. Okay. The frequency is omega naught. Of course, we know it's always easier to work in terms of this kind of A dagger A. And this denotes this A naught as 2m omega naught. Yeah, I just copied the definition of annihilation operator A naught from the textbook. It's linear in X and P. And of course, we know the energy levels and the splitting is proportional to omega naught. Okay, H bar omega naught. So as long as we now imagine I suddenly change this Hamiltonian to another Hamiltonian H tilde, which is also a simple harmonic oscillator, but the frequency is not omega naught, it's omega. And of course, we can similarly write this guy in terms of A dagger and A, but this A is different from A naught, right? Of course, as long as, okay, so assuming I prepare my initial state within like as the ground state of my original Hamiltonian. So A naught. So my initial state is 0. This 0 is the, okay, so let's for H naught, I denote the ground state as 0, first excited state is 1 and 2 and 3 and so on and so forth. For the new Hamiltonian, I denote the ground state as 0 tilde, first excited state as this one, yeah, something like this, to distinguish the thing. So the question asks you to calculate the evolution of this wave function under this Hamiltonian. Yeah. So this can be a very good exam problem. It's yeah, it's actually quite straightforward. As long as we can decompose my my initial state in terms of the new basis, then this problem is solved, right? To achieve that, that's yeah. By the way, did you guys understand this problem, what the question is asking for? Okay. Oh, yeah. Okay, so to achieve that, let's, by the way, you can try it by yourself. Maybe there's some other methods, but I think this is the simplest way to do it. So let's find the relationship between the A and A naught, because they are the key objects in those two Hamiltonians. I want to connect those two Hamiltonians. So A, according to the definition, is this. Of course, this guy is related to A naught because they are both linear position of X and P, right? If you work it out carefully, you would find something like this. Okay. Right. This step is just some algebra. It's not that difficult. You can check it by yourself. Now here's the trick. Because you'll notice that the coefficient of A naught, let's denote as A, just for this second. The coefficient of this A naught dagger, let's denote as B. We notice that A square minus B square equal to 1. That means we can denote A as a quench R and B as quench R, right? Like this. Yeah, so far so good. Okay, so this can be written in a very nice form. Here is some S dagger R A naught S R. By the way, this factor R is totally determined by the ratio of omega naught to omega, right? Because this sign R is defined by this guy. Yeah, it's only a function of omega divided by omega naught. Here I haven't defined this SR yet. This SR is called squeezing operator. It's defined in this kind of form. Yeah. So if you plug the definition of this SR operator into this guy, into this expression, you would get this quench R A naught minus quench R A naught dagger. Okay. So this is what we call squeezing operator. Okay, so there are some important properties associated with for this operator. This is a unitary operator, and S dagger R equal to S minus R. You can check by yourself. And R is the called squeezing parameter. So this is one concept I would like to introduce to you guys. That this concept is important in the community of quantum optics. So there are kind of two type of lights or lasers that often used in the quantum optics. One is the coherent light, right? Coherent light, we know what is a coherent state. Coherent state is a minimum uncertainty state, right? You can get a coherent state by displace a vacuum state, right? This is a displacement operator. And eventually you would get something, if you calculate the uncertainty in this XP, basically let's denote as phi. Phi is a coherent state, then we could calculate something like this. Something like this, I think. Or, oops, let's write this form. Under this state, you would get something like this. Yeah. Basically, you would get this is a minimum uncertainty state, and the uncertainty in the x direction and the z direction are the same. This is a coherent state, and this is the most classical state we can have in quantum physics. So in contrast to this coherent light, there is another so-called squeezed light, which construct by this squeezing operator. And as you will see, a state is called a squeezed vacuum state if this state is defined in this form. By the way, this vacuum state is also a special coherent state, right? It's just centered as an orange, and it's a minimum uncertainty state. So this state also has minimum uncertainty. It's also a minimum uncertainty state, but the uncertainty in x direction and p direction are different. That's why it's called squeezed state. So if you calculate the same quantity x, delta x, and delta p under this state, you would get, I didn't remember it's minus r or plus r, but one is minus r, one is plus r. Basically, it means eventually you would get a state something like this. It's still a minimum uncertainty state, but it's squeezed. The fluctuation, the quantum noise in two directions are different. Yeah, is it clear? That's the picture here. Okay.
So could you explain what is that d of alpha?
D of alpha is the displacement operator. It's defined something like this. I also didn't remember the exact definition, or something like this, or what? If anyone remember, yeah, something like this. You can look up on Sakura. I'm pretty sure, yeah, there's a definition of it. It's a displacement operator. I can look it up. Mm. Right, whatever. Yeah, you can. I didn't find it, but I'm pretty sure it's in the Sakura textbook, like the textbook. Yeah. Basically, uh, the state site defined in this way is the eigenstate of the nomination operator A, right? We would get alpha. So alpha is alpha here.
I have a question. So I'm just trying to understand the kind of the connection to like the actual problem we started with. I'm assuming that, so we were solving that problem for some arbitrary change in shape of the potential, but we could also say that it's changing infinitesimally, and that parameter R is kind of related to that, right? So it tells you how much you changed your shape.
Right, exactly.
Right.
Yes, yes.
Okay.
Yeah, that's true. Yeah.
Could we view the change of the characteristic frequency of the oscillator just as a rescaling of one of the two axes, and that could cause the squeezing?
Yeah, that's true. Yeah. Yeah, that's a very good point, I think. You can think of this the change of the frequency as the rescaling of your x. Then it's kind of it's like yeah, it's kind of a redefine your x-axis. Then it's noise in two directions are not necessarily the same. Yeah, that's a good point. Yeah. Okay, so this here just some mini introduction to this squeezed and coherent issues. By the way, the squeezed net is important because it's a non-classical state, meaning that it always associated with some quantum entanglement. That's why it's widely used in quantum optics and. Okay, so okay, so yeah, well, we find the relation between A and the A naught. Remember, A naught is the annihilation operator for the original Hamiltonian, and A is the operator for the new Hamiltonian. And the purpose, the goal we want to achieve is to find is to find the decomposition of my original ground state in terms of a new basis, right? Okay. Okay, so let me write down this expression. This is the only equation we achieved so far. And of course, this means A naught equal to S R A S R, right? I can inverse the relation by invoking this unitary property of this S operator. What I want to say, right. So the original ground state is defined by this differential equation, right? This is the differential equation because A naught is a superposition of x and p, the differential operator. So yeah. And now we know A naught is nothing but this operator. Now I'm trying to do it in a smart way. I'm pretty sure you can solve it like in a brute force kind of a derivation. But let's look at this by invoking this squeezed operator. Right? Here I just replace A naught with the expression here. And to make sure this guy is 0, the only way to make this guy 0 is this part is the ground state of my new Hamiltonian, right? That tells us there is a relation between my original ground state and my new ground state. This is also not difficult to imagine. It's like what you point out, I have some original ground state configuration. Now I reparameterize my x-axis. That's equivalent to squeezing the state, and I get I get my new Hamiltonian, and it's not difficult to imagine those two are related by some squeezing operator. Yeah, so if that's just a hand-waving argument, but if you work out this kind of algebra rigorously, you will find the relation is exactly like this. Yeah. So on the left-hand side is the original ground state. On the right-hand side is the new ground state. Is it clear about like all the argument I used here? Okay, so, and you can say this is just nothing but the squeezed vacuum state, right? It's the squeeze operator acting on a vacuum state. So it's called squeezed vacuum. And right, if you, okay, you can work out this guy using the definition of this S operator, but I just look up on the quantum optics textbook. This guy is nothing but some complicated series, which is like this: 0 plus infinity. So now we achieved our goal. Basically, we expressed our original ground state in terms of the new basis. Yeah. Then the evolution of this state under the new Hamiltonian is very easy, right? You just add this kind of exponential factor into the prefactors of this eigenstate. So everything is clear. Let me know if you have any questions or comments.
You make a parity argument for why we would only see the even states?
Okay, so that's that's a good point. I'm going to say that the specific coefficients is not important. What's important is this state only invokes an even parity state. Right. That's also one kind of feature of the squeezed vacuum state. And in our specific example, it's very easy to argue, right? because my original state is the ground state of my original Hamiltonian. It's a even parity state. Of course, if you decompose this state in terms of the new basis, it's still a even parity state. So it's still even like in terms of the superposition of all the even parity states, new basis. Right.
So from those cosine HR to the S operator, did you do we just plug in and convince ourselves, or?
Oh, you mean sorry,
The
where to where?
It's above, on the above.
From this one to here,
No,
or
no, like the one where you introduced the S, the
oh, here I say from this guy to here. Yeah, you need to. This is a one. This is a one like important equations associated with the squeezing operator.
So we just memorize them and plug in to convince ourselves.
I mean, you can also prove it, right? It's not difficult to prove. We just use the it's like something like this. Yeah, use this. There's a formula related to this type of calculation, right? I didn't remember exactly, but you do the computation. Basically, it boils down to calculation of the A, B commutator and A, B, like a B commutator, something like that.
Okay.
Yeah. Also, when you do the Bogoliubov transformation in superconductor, you would also and you will also encounter this type of transformations. You can see this. Okay, so this is the one part I want to discuss. Okay, so another part is about linear response. Okay, linear response is even more important. Okay, especially for Commons matter. Okay, so the general goal is like this. Imagine we have some system. You can think of it as a kind of a black box, and we don't know what's the ingredients within the box, and yeah, we want to somehow get the information of this material or whatever the system is. The way we do it is apply some perturbation and see how the system will respond to the external perturbation. That's how we perturb, like how we probe our material or anything we're interested in. Right? So to describe this process, this procedure, we developed a kind of theory, and it's just nothing but a linear response. Okay, so let's start by writing down the Hamiltonian. Imagine H naught is the Hamiltonian of my system. It can be very complicated. There's no reason this is solvable. In generally speaking, there's no exact solution. And this guy is the perturbation or the drive we apply to the system. For example, we can apply electric field, like a AC electric field, oscillation electric field. Then this part is just the scalar potential, right? Like act electric field as a function of time and coupled with the position and some charge. We can also apply the magnetic field. Yeah, it's just an example. Then we want to measure a quantity A. We know the quantity in quantum physics is represented using the quantum operator at time t. How this guy evolve? So this is the question we want to ask. On the drive, we use the Heisenberg picture, meaning that the density matrix, of the system is constant. Then we apply the drive. In this case, my operator A, the quantity we care about. For example, if we apply the electric field, we want to say this A would be our current operator. We would want to measure the current. Then, okay, so this current is equal to something times my perturbation electric field. The coefficient is nothing but the conductivity of my material, right? Okay, so my A operator is in the Heisenberg picture, meaning that my A operator evolves according to H0 plus H prime. On the other hand, we know this A operator in the Heisenberg picture is related to the A operator in the interaction picture, where this guy, this is the T tag 0. Yeah, I think you have seen this. Yeah, by the way, this guy, you can find the expression is a time ordered T naught, T E T prime, H prime, and this guy is also in the interaction picture, prime, something like this. Yeah. In the time dependent perturbation, I think you have seen this, right? Yeah, that's the reason why I put this linear response here. I think it's a good position to introduce this. Okay. By the way, the point is this guy evolves according to H0, meaning that this A, I, T, under the take this average, this is nothing but the average, how to say, the value of A in equilibrium when the system is in equilibrium in the absence of the drive, because this guy evolves according to H0. This guy is the value. What we will measure is the value of A at time t under the drive, and we want to compare the difference of those two. Usually, for example, if we care about the current, this guy, in the absence of the drive, we would expect this guy to be 0. There's no current. Once we apply some electric field, to drive the system, we will see some current. A linear response means this drive is weak, so we can apply the approximation like that to first order. So this guy is approximate by this. Similarly, this guy can be approximate by this. Right. And you expand this guy in to first order, you would get here just some simple algebra. By the way, here I'm not doing a specific problem. I'm providing a framework to study a type of very general problems. Like this, right? You should be able to derive this equation by yourself because all the ingredients are known from the time-dependent perturbation discussion. Now we take an average. Take an average. This guy depends on time, but okay, so remember this guy, because is in the interaction picture, meaning that it evolves according to the original system Hamiltonian. So it's kind of an equilibrium property of this operator A. And we denote the difference of those two as the, so let's introduce this guy. This guy is the difference of this operator A under the drive and operator A in the equilibrium. This guy is T90. I will drop this operator, this index I, just for convenience, like this. As you will see, what we will introduce is the so-called retarded Green's function. And that's the quantities we usually calculate in condensed matter theory. Right. So far, so good. Yeah. Feel free to let me know if you have any comments or questions. By the way, this H prime usually is in this form, right? It's lambda t and times the operator, let's say it's B. So remember, in our electron field case, the lambda is the electron field, which is just a classical parameter, which we can control. We have a control under this parameter lambda. And B is the operator we coupled to. It's an operator within the system. Right.
And for electric field, that was x, right?
Yeah, exactly, yes. And this is, remember, this is in the interaction picture. Something like this. Okay, so it would say we can even make this expression looks much nicer by use the fact that we turn on this drive at time t0, meaning that when this t is smaller than t0, is 0. That's what we did. That's what we will do in experiment. We have equilibrium, a system in equilibrium. Then we turn on the drive at some time. Then we measure the system, how the system responds to that drive after we turn on, right? So we can extend this T0 to minus infinity because there is a lambda factor here. And we also want to extend this T, which looks very ugly. So we just put it into infinity and introduce the step function, which is T minus T. And let's rearrange several terms. Right. So this is what we call the retarded Green's function. This is the definition. And so I have this. Right. And this retarded Green's function is also known as a response function, right? Retarded response function, or yeah, this is just a convolution of the time. If you go to the frequency space, this even looks much nicer. Yeah, if you think of this number as an electric field, this guy as the current we will measure, then it's just this coefficient is just conductivity of my system, which will depend on the frequency, right? You use to drive the system. Yeah, you can use this kind of this is just general formalism. You can use this philosophy to calculate many different quantities that you measured in experiments and yeah. Okay, so this is a linear response. The point is all the response measurements will boils down to this kind of a Green's function. So from the theoretical point of view, the only quantities we need to calculate is this guy, is the Green's function. But this guy is not easy to calculate in general. Remember, this A and B are evolving according to the Hamiltonian H0. H0 is the Hamiltonian of my system, which in generally speaking can be very complicated, which definitely beyond one body interaction, like one body Hamiltonian in many cases. And yeah, that's why we need to introduce some perturbation. So when we calculate this guy, we also use the perturbation within the Hamiltonian, separate the Hamiltonian into some easy part and the difficult part, and expand the difficult part using Tanner series. And then we have some techniques to solve it, like Feynman diagrams, which quite similar to what we did in the quantum field theory A. You will learn in quantum field theory. Okay, so that's what I want to say about the linear response. Any comments or questions? Yeah, if not, you're free to go.
So in here you arrived at this Ohm's law basically because you assume that we have linear response, right? The
right.
Perturbation is small.
Right. That's a very important assumption. Okay, let me end the